one of the key ideas in linear algebra is the concept of a transformation. And transformations can take many different forms, from, for example, a matrix being multiplied by a vector to give you another vector that can transform one world of vectors, say, into another world of vectors. But before we start thinking about it from that standpoint, let's look at it from a much more basic idea that's common to some of our experiences even in, say, high school algebra or high school physics. Imagine that we are at a grocery store. You're in the produce aisle, and in the produce aisle you'll see scattered around various measurement devices for measuring the weight of the produce. So for example, here I've created a little scale, so to speak, using a spring and a little basket that I can put things in, for example, like my zucchini from the grocery store. I also have some masses that I know the exact measurement of their force as well that we'll play around with here. So the idea that we're going to use, and the idea that all scales basically use, is this idea of what's called Hooke's law. And in Hooke's law, it states that the force is proportional to the stretch on a spring. In this case, we're using the spring where you can clearly see the length of it, because we're going to look at the displacement of the length. And you can see I've got measured, the top value is in newtons, that's the force being measured by this force probe. And the bottom number is the position as I've got measured with a motion probe on the floor. Now what we're going to do is we're going to look at the displacement of the spring as I add masses to it, and we're going to look at the corresponding force relationship that comes out of it. In physics, you actually may remember thinking about this as a force as a vector by putting a little harpoon over it. Same thing with the position, x, because we think of those as single entry vectors, so to speak. Well, in this case, I've got some masses here. I'm going to put a mass in the little dish that I've got down here. I'm going to have to wait for it to kind of stop swinging a little bit. You'll notice that I've got a force measurement and I've got a position measurement. My position might look a little odd because it's got a negative in front of it, but that's because it's measuring the change in distance from the original position of the pan balance down to where it is now from the floor. So it's going to appear negative, but it's really corresponding to a positive stretch. So in this case, I've got a measurement of stretch somewhere around 0.06. And the force that goes with that is about 1.9. It's fluctuating because of movement. About 1.9, let's say 9 newtons. So close to 2, okay, which is actually good because we're going to estimate here in a minute. So if I put another identical mass in here, what would be the prediction for the force and the stretch? So I have, in a sense, doubled it. So my stretch now should correspond to about double this, which it does. My stretch is now about 0.117, say, which is approximately 0.12, which would be double 0.06. Okay, my force went from 1.99, essentially about 2, to about 4.00, see if it settles down here, 2, let's just round it and say. So and essentially this is about 2 newtons, this is about 4 newtons, and so we see that if I double the stretch, if I double the mass, so to speak, that's in there, the stretch doubles and the corresponding force also changes in suit. So for example, if I think of this as a transformation, I can say that if I take the transformation, I'm calling it T, which is our force, that if I double the stretch, I should get the same thing as if I doubled the force that was on the original amount, being 2. So here, I end up basically preserving scalar multiplication. So scalar multiplication gets preserved under this process. Now, that's all well and good if I'm doubling, tripling, quadrupling something, but what if I have things that are of different masses? So let me pop these guys out of here for a minute. Let that settle down. So here, suppose I have 2 clearly different size zucchini, right? And I go to the store, and I put 1 zucchini in here. If I can balance it. Call that x, and our force here will be our transformation of x. So in this case, my stretch corresponds to about 0.98, let's say. Whoops, 0.098, my bad. 0.098, and the corresponding force that goes with that is about 3.3 newtons. Okay, so now if I take this zucchini off, and I put this other zucchini on, get it to balance. To stop moving around too badly. I get a stretch of 0.52, let's say. I'm sorry, I keep opting to forget the 0. 0.05. I'll say 5.5. And then I get a stretch of about 1.77. All right. So what should we predict based on the linearity of the situation with Hooke's law if I put both on together? Now, if I add these guys up, if I add about 0.098 to 0.055, I should get somewhere in the neighborhood of 0.131. Balanced. They're not quite balanced. The basket was off just a little bit. Because they're not the same mass, they're tipping the basket a little bit. So I'm off just a tad. But it's somewhere in the neighborhood of 0.13, say 3. And over here, I'm getting a total force of about 5, which is about the same as if I added these two up, because this would be 5 point, if I add that, 0.07. So I'm going to get about 5.07, which is about what we're reading on my measurement there. Part of the problem, and I can see it here as I look at the pan balance, because one of the zucchini is larger than the other, my pan balance is tipped. So the bottom of it's not quite flat, but you'll notice that this is approximately the sum of these two, and this is approximately the sum of those two. So the two basic principles that we have working here is I've got the preservation of scalar multiplication, and I've got the preservation of what we call vector addition. So if I take the transformation and I add two things in, let's call them x and y, I get the same thing as if I weighed each one individually and added those together. So these two principles together, scalar multiplication is preserved, vector addition is preserved, are the two characteristics that we have when we talk about a linear transformation. In this case, we're actually transforming just basic things like stretch of a spring to a force or a weight, but it can also happen when you talk about principles like mapping one type of vector into another type of vector in, say, three-dimensional space. So those are basically the two big ideas that we need to define what a linear transformation is.